Hello, my name is Shamser Ahmed. I work on the HPCC platform team. Today, I'd like to talk about cost savings on the cloud native systems using ECL metrics. ECL cost metrics. One of the benefits of moving to the cloud is the huge flexibility that the cloud presents. However, in providing this flexibility, there is the opportunity to incur unexpected costs. The cloud presents an opportunity for ECL developers to directly impact the cost of the services that they design and produce. Queries, datasets, infrastructure, these can all be designed in a way that reduces costs and improves performance. The cost information provided by the cloud provider is not usually sufficient to be useful to ECL developers. They're not detailed enough. They provide broad information rather than specific information about jobs that ECL developers are working on, work units and queries that ECL developers are working on. So the ECL cost metrics are designed to help ECL developers to decide on which areas to focus on for improvements. For example, high cost areas may be examined more closely to see if there's scope for reducing costs there. After examining costs, there may be activities or storage that are found not to be as useful as originally thought. There may even be storage that's used for future functionality, but not necessarily now. There may be also, the stats will also highlight opportunities to change storage types to more appropriate storage types. For example, would premium be more suitable or hot being more suitable? These, in some cases, cold would be sufficient. So the stats should provide information to allow developers to make decisions or in this area. Also, for example, there may be infrequently used data that could be compressed. Stats will also assist developers in troubleshooting and proactively investigating their work units. The for example, sudden change in costs may highlight a problem with data or queries. A job may cost more than estimated. Storage may cost more than expected. So has there been a misassumption made when the architecture was designed, or the query was designed, or the data set was designed? What aspects need to be revisited? So the ECL cost metric should help with these areas. The cost metrics are also useful to other persons, DevOps, architects, managers. They can see what the actual cost is of providing a particular service, where the main costs are in providing a service. Maybe something could be designed slightly differently to reduce the cost. The infrastructure itself, for example, the cluster size or the number of nodes, the number of CPUs, networking, the use of child processes, etc. These all affect the cost of the work, the jobs that the designers, architects, managers implement. So changes can be made in these areas to reduce costs. They can also look at balancing spin up versus idle resources. Spinning up takes time, but is immediately available. Idle resources, spinning up takes time, but doesn't cost anything. Whereas spun up resources are idle and are costing money, but they are immediately available. Another thing that may be useful is comparing the cost of in-prem data center with the cost of hosting in the cloud. So the is not necessarily a primary factor, but it may help in seeing how much less or more the cloud services are costing. These are the ambitions for the ECL cost metrics. Useful functionality is already available as of 8.8. More improvements and features are planned to deliver these extensive goals. The costs in the cloud. To understand the cost metrics as presented within the platform, it is important to understand how HPCC platform deployments incur costs in the cloud. HPCC platform cloud native version is deployed, scaled, managed by Kubernetes. That is important. Components, although Kubernetes itself doesn't incur a charge, the worker nodes that Kubernetes uses to deploy the HPCC platform to does incur a cost. Persistent information stored in storage accounts also incur costs. Persistent information includes things like logical files, work unit DLLs, drop zones. There's also charges for storing the data, accessing the data, and possibly for the data transfer. Data can, of course, remain on-prem or with a foreign cloud provider. These will not be tracked by HPCC. There's also other charges involved in the cloud deployments and public IP address, proxies, registries, other things like this incur a charge but are not tracked by HPCC. And we don't plan to track these. So in examining the cost metrics, it's important to understand that there are costs that are not factored in the metrics. So what costs are tracked? With ECL, every ECL job, the two types of costs being tracked, the execution cost and the storage costs. Execution cost is the cost of using the worker nodes in the node pool to complete the job. Execute costs will be referred to as cost execute in the ECL stats. Storage costs are incurred for hosting persistent data with the cloud provider. As mentioned, persistent data includes logical file storage, work unit DLLs, DALI, drop zone storage. Of course, logical files on-prem and other locations are not tracked. Storage cost includes the cost of hosting every gigabyte of persistent data by the cloud provider. These are referred to as at-rest costs in the ECL cost metrics. There may be a charge for every read, write, delete, index, and other operations. These are collectively known as file access costs or storage operations. Storage operations are tracked both by the ECL jobs and by the logical files or at the logical file level. Storage file operations that are recorded with the ECL job relates to the cost of the storage operation incurred by that job. Whereas the storage operation under the logical file is for all the storage operations that occur against that logical file. There may also be data transfer costs. For example, reading from core storage or copy of data between regions. With Azure, there is no transfer for reading from premium or hot unless the data resides in a different region. Data transfer costs are not tracked at this time by HPCC, but we will look at including that as well. It's a little bit more complicated as the cost varies depending on where the source and the destination is. One point to note, jobs also use temporary files. So for things like spills, these do not incur additional charges if they use local storage and are also not tracked by ECL, by HPCC. Job execution costs. So VM resources are used to execute Thor jobs. Some Thor jobs, some components used to execute the Thor jobs are specific to that job. So like Thor manager and Thor workers are spun up to execute just that job. There are also jobs that are shared, such as DALI, ECL services, DFU server, Roxy. These are always shared, and the cost of, although they're incurring costs, the cost of using them do not or will not show up in any of the cost stats. We are attempting to improve the stats further so that the file operations DFU server generates some cost information as well. There's other components which may be job specific or may be shared. For example, ECL agents or HTOR may use child processes in the main shared pod. So this cost is not an additional cost for the for job, and it may also be configured to spin up a pod, a HTOR or ECL agent or ECLCC pod specifically for the Thor job. These relate to the job and should be included with the job. So so these costs are sometimes included and sometimes not included. We're always interested in the costs in the first column. We're not interested in the costs specifically for the job in the third column. The second columns are sometimes included, depending on how the system is configured. So if you have, for example, HTOR configured to use child processes, that shouldn't be included in the job specific costs. So how is the execution calculated? HPCC Cloud Native separates functional HPCC components into Kubernetes pods. Kubernetes deploys these pods to nodes within the node pool based on the resource requirements and constraints specified in the configuration YAML. So that means the multiple components may share a pod. To calculate the execution costs, we need to know how much that VM or compute node costs. We need to know how much of that VM is being used for that job and how long it uses that pod. So if we have those three pieces of information, we can work out the cost of a component. And if we sum up all the job specific components costs, we can arrive at the total cost. The hourly cost in the node of each node in the node pool has to be configured in the configuration. HPCC doesn't determine that. So if the rates provided is wrong, then it would produce inaccurate cost calculation. So simply, HPC job execution costs for a component is calculated by getting the hourly cost of a component, the time the component has been active, and the number of cores that that component uses. So we are using the number of cores to determine how much of the node the component uses. So if we sum all the active components, we get the job specific cost. However, there are some complications which we will come to. Okay, here's an example of the node pricing at Azure. This is the B series node pricing, compute node pricing. They're designed for testing, development, and small, medium-sized applications. There's other nodes, many other nodes, and nodes for different purposes, machine learning, high disk throughput, performance. So it's not possible to configure exactly what the cores, RAM, temporary storage individually, but there should be a close match to what's required. The pricing, to calculate the core pricing, we can take B16 compute node as an example. It has 16 cores and it costs $486.18 per month. That means each core costs just over $30 per core per month. And that means about over 4.38 cents per core per hour. We can use those figures to work out the cost, which I'll come to. So here we have a node pool of 4 B16 MS compute nodes. Kubernetes deploys components across the node pool based on the resource requirements So DALI could say, okay, it needs 14 cores, so it gets a big chunk of node 1. There could also be making use of taints and affinity, so the 4 workers end up in a node together. However, this management deployment of nodes by Kubernetes is likely to leave unused resources, unused cores. It may not be possible to efficiently make use of all the cores across all the node pools because of the requirements, resource requirements. These unused resources are still charged for, but as far as the cost metrics are concerned, then they're not considered at all. So they're not considered in calculating the total cost of the components. So not all cores, to summarize, job costs not tracked. So with all cores not being unlikely to be used, the full cost of the nodes will not be tracked. Also, components, when they come up, before they're available, some time is taken. And when they're shut down, terminated, that takes time as well. So during that time, costs are incurred, but they're not tracked. They won't show in any of the cost stats because simply HPCC doesn't know about that time. For example, HPCC manager will work out its time from the beginning it's available till it's finished the last graph. So any time outside that will not be tracked. Pods may be set to linger. That means pods may be set to hang around a bit longer to avoid the spin up time. This time where the pods is lingering, it's idle, but again, these idle costs will not be tracked. Roxy is another area where we're not tracking costs. Roxy is the way it's architected, the resources are all shared, and it's difficult to isolate specific resources used by a specific Roxy job. So at this time, we're not attributing any Roxy costs. We're looking at how we can include Roxy costs in the stats as well. There's other job relating costs that are not tracked. So copy, spray, despray. These are something we're looking at including. But there's also things like ESP services. So if a Thor calls out to an ESP service, it incurs a cost, but it won't show in any of the stats. We've covered this briefly. There is an issue of double counting. If resources for a pod is shared, then there is a possibility of double counting. So we've tried to avoid that, but there is still some double counting as far as some of the resources go. Okay, the other thing we need to look at is how storage costs are handled. Local storage is provided with the compute node, usually. The storage is effectively free because they are included with the cost of the VM. Local storage are used for spill files and other temporary storage. So when you're examining the cost metrics, you will see in the ECL graph or the metrics that the spill files do not generate any costs at this time, the storage costs or operations costs. However, there are some VM types that where local storage is not available, or there may be cases where it's preferable to use mounted remote storage, which is chargeable. So there is a possibility that the assumption that temporary files are effectively free is not always true. We're looking at that, and we should provide the possibility of tracking the cost of temporary files as well. Persistent data always needs to be stored somewhere outside local storage, usually with a cloud provider. That persistent storage will incur costs, the main ones being cost for the price per gigabyte per month. We're tracking this cost for logical files. There's also operations cost, which is cost of read, write, index, any request made, that also incurs a cost. And again, we are tracking that for logical file, and work units also track how much operations costs it generates. Data transfer costs may apply in some cases. They're usually free for premium and hot, but that's not always the case. For example, across regions. We're not tracking this presently because it's more complicated, but we'll look at tracking data transfer costs as well. Reducing storage relating costs. Obviously, using the appropriate storage types is important. Sometimes premium is appropriate, sometimes hot storage or even cold storage is more appropriate. So hopefully the stats will aid in deciding what's most appropriate. The cost of data transfer is not always free. So between availability zones and regions, where the data is located needs to be considered to avoid transfer costs. There are also some changes that may be made with the HPCC configuration to reduce the data operations costs. A copy, spray, despray with the current method is carried out block by block. A large file may have tens of thousands, hundreds of thousands, or even millions of blocks. That will mean that many requests needs to be made to complete the copy, spray, despray operation. One way of reducing this cost is to increase the block size. So increasing the block size, for example, from 64K to 1 megabyte will mean the number of requests reduced by a factor of 16. Number of requests required to carry out the operation will reduce by a factor of 16. This should substantially reduce the cost of these operations, as every request incurs a cost. The for file read and write activities may also benefit from a larger block size. There's another feature that has been recently introduced, which may reduce the cost of copies, sprays, desprays. It's using the cloud provider's API to carry out the copy. API copy makes a single request to, for example, the Azure, the cloud provider, to have the entire physical file copied. It also is possible to have parts of the file, big chunks of the file, copied in a single request. This will reduce the operations, number of requests made to the storage account, reducing the cost of the spray despray copy. But in addition, it's much faster. So storage costs are also not all storage costs are tracked by the platform. So it's possible to access files in the storage account directly, bypassing HPCC. These costs, if HPCC doesn't know about it, won't be tracked. And I've mentioned before, chargeable data transfer costs are not tracked. There's some operations that are not tracked at this time, the cost of which is not tracked. Indexing, deletes, etc., they're not tracked. I suspect these are very small number of operations and would not affect the overall cost by anything that's significant. And there's some data that's being stored in the storage accounts with the cloud provider that's not tracked. And there's also storage costs that may be double counted. Cache files are read once, charged for once, but if they're read multiple times through the cache, it may appear that multiple charges are being incurred, but actually there's been just one charge for reading that file. Also, the OS and, for example, the remote device driver may cache files. There's also a possibility that a small request is, so a 64K request is automatically read, submitted as a much larger 1 megabyte or 2 megabyte read request. And again, for that reason, the cost may be overstated. There's we do have some storage cost issues that we're addressing, that we plan to address. Deleted files may be logic files may be deleted, and a new file may be written with the same name. The file's cost stats will show the cost of the new file, and it won't accumulate the cost from the previous deleted file. So the original costs associated with that file is lost. Work units will still show the file access cost that it's generated, whereas the new file will show the file access since it was deleted and recreated. So access costs shown for files in the work unit will not necessarily make sense when compared to newly created files. For example, the access cost for the work unit may show a very large access cost, whereas the newly created file will show the access cost since. So it could appear that the entire access has been from one work unit. So it can cause confusion whilst troubleshooting. So this is something to be aware of. There is a case for showing historic costs, and there will be some work done in this area. HPC cache is an Azure file caching service that caches data from Azure storage or on-prem storage. It improves performance by reducing latency and reduces costs, because every additional request to the cache doesn't incur any additional cost. Only the first read from the storage account to populate the cache incurs a cost. HPC cache is charged on a per hour basis for the chosen cache size and throughput. So, for example, a 1 terabyte HPC cache is fixed whether the cache files is 200 gigabytes or 2 terabytes of cache, of files being cached. The hourly cost is fixed. Each access of files from HPC cache doesn't incur additional costs, so it's not possible to sensibly attribute HPC cache to a work unit. HPC cache causes further issues with the file cost information, because the cache itself is populated from the storage, and as the data is read from Azure storage, to populate the cache, a cost is incurred from reading the Azure storage. This cost is not reflected in the logical files cost stats. Access costs caused by accessing logical files that bypass HPCC will not be reflected in ECL Watch file access costs. So this is Azure's cache, HPC. It's a similar name to HPCC. So forgive me if I've used the name wrong previously. Okay, cost stats in ECL Watch. So this is in the ECL Watch's work units page. You'll see that there are 2 new columns. One for execution costs and the other for file access costs. These columns are, if you can't see these columns in your interface, you need to enable the tech preview to show the new ECL interface. The file access cost is the cost of the cost incurred by this work unit in accessing the file. Work unit costs may also be viewed in the summary page. Execution costs, you can see, is right at the bottom, and the file access cost is there too. The graph can be examined to to drill down and find and locate the source of a large cost. Here the graph is showing a cost, and drilling down further, it shows the subgraph where the cost incurs, and drilling down further will show that this right incurred the cost. Each logical file at rest and access cost is tracked and can be viewed in the ECL Watches logical file page. So you can see the last two columns, file cost at rest and file access cost. These costs, like the work unit, is also shown in the summary page for the logical file. So here you've got the file access cost about 10 cents and the at rest cost at $124.6. The at rest cost will be updated continuously as the file ages. Every time the file is viewed, the at rest cost will show the current cost of hosting that file at the cloud provider. The cost, all the cost metrics require some cost parameters to be provided in the configuration YAML. The hourly cost of each core in the node pool has to be configured in the HPCC configuration. That's per CPU field. HPCC cannot determine the hourly cost automatically, nor can it determine the actual cost of storage or the cost of the reads or the writes. These needs to be provided in the configuration. If these are the defaults provided, however, if these defaults are used, it's unlikely these costs, the cost shown in the cost matrix will reflect the actual costs incurred with the cloud provider. So the costs should be updated. So say the node pool is made up of B16MS compute nodes, which are charged at $486, 18 cents per month. Then the cost per core, or cost per CPU, is 4.38 cents, and that should be, so the per CPU should be updated to reflect that. The third field is the at rest. That's the cost of storing a gigabyte of data for a month. And the fourth is the cost of 10,000 read operations. So here we're saying 10,000 read operations are going to cost 4.85 cents. And similarly, for storage writes, every 10,000 write operation, how much it will cost. So 0.3 cents for 10,000 write operations. Yeah. So these do need to be updated to reflect the actual costs. It's possible to use affinity and taints so that components are located in nodes with different configurations, with different costs. So under each component, it's possible to override the per CPU cost with a different cost value. So this will override the cost provided in the global per CPU rate. There may also be multiple storage planes mounted on different types of storage, which each have different costs associated with them. So here, it's possible under each storage plane to provide a cost. So it's possible to have every storage plane with a different cost, and these will be tracked correctly. Okay, so as a feature of the cost metrics, extending on from the cost metrics, we've implemented a job guillotine feature. Job guillotine allows a cost limit to be set that, when exceeded, will terminate the job. This would be especially useful for ensuring jobs don't exceed the maximum cost level, and it's invaluable for stopping overnight jobs from runaway costs. So here you can see right at the bottom, this job has been terminated because the cost threshold has been exceeded. Is possible, the threshold for terminating a job may be set in the ECL through the max cost option. Here is set to 10.00, which is $10. So if this query exceeds $10, it will be terminated. Some defaults for the guillotine, job guillotine, may be provided in the configuration YAML. So the limit is the default termination threshold. So it's $10. Any jobs, unless a higher max cost has been provided, will be terminated at $10. Hard limit is similar to the limit, but it cannot be overridden by max cost. So these limit values are in whatever currency is defined in the values YAML. If USD has been defined as a currency, then the first limit is $10. It's not compulsory to provide a cost guillotine section. If it's not there, then the default job guillotine is disabled. However, individual ECL jobs can still set a max cost value. The use of cost feature in bare metal requires some creativity. The on-prem has high fixed costs, so you pay for all the hardware and you set it up and spend hundreds or millions of dollars, and it's fixed. But incremental, the cost of running each new job is minimal. It's basically the cost of a little bit of extra electricity or air conditioning being used. So there is some creativity required to use the cost feature within on-prem. So there could be a way of calculating the huge upfront cost by immortalizing the cost over the lifetime of the cluster and calculating the cost per CPU. But that also it needs to reflect that inactive cluster still needs to be paid for. So although a cluster may be active 50% of the day, 12 hours a day, the 12 hours that is inactive is still a cost and needs to be reflected in the active hours. And then all the staffing costs and literacy and other variable costs needs to be factored in. So on-prem storage, the cost of that needs to also be provided in the cost structure for the cost configuration. And again, the cost per gigabyte needs to be calculated. Again, taking into account that unused storage still costs money and needs to be paid for. So to use the cost feed share on-prem is a section needs to be added under the hardware, environment hardware section. Environment hardware section. Same values, same structure. You need the currency code, the per CPU or per core cost, storage costs, at rest, reads and writes. So this can be used to provide indicative cost for using on-prem for either storage or jobs. So planned improvements. There is a lot to do. There are significant opportunities to improve the cost information. We do have quite a few features that we have planned and improvements that we'd like to make. So a priority is to improve the cost calculation. Improve the cost calculation to make sure it reflects the actual cost being incurred at the cloud provider, with the cloud provider. We have plans to include the cost of spraying, despraying, and copying files. We need to work out somehow how to include the HPC cache costs, Azure HPCC cache costs. I believe actually the compilation costs are being tracked and included as part of the total execution cost. So we may present that separately. DALI incurs costs, again, include that somehow, report that somehow. Deleted work units and deleted files. So these we don't want to lose cost information from deleted work units or files, and we need to retain that somehow because it may be invaluable in diagnosing problems and investigating cost issues. We'd also like to accumulate cost by user. So the user can see how much the jobs that they generate costs. We would also like to extend the guillotine feature so that the jobs can be suspended rather than simply terminated. So if a job exceeds a threshold, it could be suspended and then re-examined and resumed if decided. We'd also like to get some cost information from Roxy. Roxy has to anyway update the file access costs information, which is not being done at this time. So that is a priority, but also we'd like to get some cost information for Roxy job execution, something that makes sense. So I hope that you found this cloud cost saving presentation useful. I have a blog that's a few months old that you can examine for some details. Things have moved on, but I will look at updating this blog shortly. If you have ideas or questions or improvements that you'd like to suggest, feel free to email me. Thank you. Thank you very much for attending this presentation.